In order to examine the strength of materials under constantly changing load, the so-called fatigue test is carried out. In this test, a sample is periodically subjected to tensile and compressive stress with a certain stress amplitude. The cycle through which the sample is subjected to a complete tensile and compressive load is referred to as a load cycle. It is now measured how many load cycles a sample can withstand until failure. By testing several specimens at different stress amplitudes, the stress cycle curve, also known as the Wöhler curve, is created. This graph shows the allowable stress amplitude as a function of the number of load cycles to failure. The graph can be used to determine how many load cycles a sample can withstand at a given stress amplitude. For example, a stress amplitude of 500 newtons per square millimeter will give a number of load cycles to failure of 6,200. The number of load cycles to failure is of course not the result of the test on a single sample. Due to the variation in the quality of the specimens, the number of load cycles to failure can vary considerably despite the same stress amplitude. An exact prediction after how many load cycles a sample will fail is therefore not possible. The number of cycles to failure given in the Wöhler diagram is based on a statistical evaluation of many individual samples tested at the same stress amplitude. The indicated point on the Wöhler curve should therefore be interpreted as the probability that a specimen will fracture at a given stress amplitude. In the case of a 50% probability curve, a point on the curve indicates that a sample reaches the respective number of load cycles with a probability of 50%. This means that half of all samples will fail before reaching this number of load cycles, and the other half will withstand higher numbers of load cycles. With the given stress amplitude of 500 newtons per square millimeter, half of all samples will therefore have failed after about 6,200 load cycles. The determination of such failure probabilities can be described with the so-called Weibull distribution. The Weibull distribution is used not only in the fatigue test, but generally in reliability and survival analysis of components. Such a Weibull distribution makes it possible to model the lifetime or time to failure of components or systems. In this video, we therefore take a closer look at this form of distribution and use the fatigue test as an example. In the following, let's look at a fatigue test with a total of 20 samples that were all tested at the same stress amplitude of, for example, 500 newtons per square millimeter. Such a sample size of 20 specimens is actually too small for a valid statistical statement, but for the sake of clarity we will limit the consideration to 20 samples. The table shows the sample number and the respective number of load cycles to failure. For reasons of clarity, we first sort the column of load cycles in ascending order. This makes it easier to see at which load cycles the individual samples have fractured. The consecutive rank numbers correspond to the total number of samples that have failed up to a certain number of load cycles. So the first sample breaks after 1,041 load cycles and the next after 2,114 load cycles, so that when this number of load cycles is reached, a total of 2 samples have already failed. After 5,083 load cycles, the 8th sample is broken, so that a total of 8 samples have been failed by then. Finally, after 15,565 load cycles, all 20 samples are broken. The total number of samples that have fractured up to a certain number of load cycles is also referred to as cumulative frequency. The result of the test can be represented by plotting the cumulative frequency of fractured samples as a function of the number of load cycles. The dashed line indicates the typical course of the cumulative frequency. It is typically S-shaped, which would have been more obvious if significantly more than 20 samples had been tested. Another representation can be derived from this graph. This is done by dividing the load cycles into equal intervals, in this case 2,000 load cycles, and looking at how many samples have failed within these intervals. For example, within the first 2,000 load cycles only 1 sample fails. Between 2,000 and 4,000 load cycles 3 samples break, and between 4,000 and 6,000 cycles a total of 5 samples fracture. In the following intervals the number of broken samples decreases. This gives the frequency distribution of samples that have failed within certain intervals. Such a discrete distribution of values is also called a histogram. It is immediately apparent from this histogram that the fractured samples are not normally distributed. This means that there is no symmetrical distribution around a certain mean value, as would be the case with a Gaussian distribution. The dashed line here also shows the course of the distribution if the fatigue test were carried out with a sufficiently large number of samples. Note that we can easily convert the 2 different ways of representing the measurement results into one another. We can determine the broken samples within a load cycle interval by subtracting the respective cumulative frequencies, as we have just done. We can also determine the cumulative frequency by summing the individual frequencies up to a certain number of load cycles. Mathematically, this summation corresponds to integration in the case of a continuous distribution. In the reverse case, this corresponds to differentiation, so that by later differentiating the cumulative frequency function with respect to time, we obtain the frequency distribution. Both forms of representation so far only refer to a concrete number of samples. However, with a sufficiently large number of samples, this can be generalized to any sample size. One then no longer speaks of a concrete number of broken samples, but of a percentage of fractured samples. In our case, for example, 1 out of a total of 20 samples broke within the first 1041 load cycles. Assuming that this is a representative result, it means that 5% of all samples fail within 1041 load cycles. A total of 8 specimens broke at 5083 load cycles, representing 40% of all specimens. For generalization purposes, it is therefore useful not to give the absolute frequency of failed samples, but the relative frequency, which gives the percentage of failed samples. Of course, such a generalization presupposes that the fatigue test is carried out on a sufficiently large and therefore representative number of samples, which we assume here. At this point, the relative frequency can also be interpreted as the probability of failure. For example, if 25% of the samples are fractured after 4,391 load cycles, this means that 25 samples out of a total of 100 samples will fail. Therefore, if a sample is randomly selected from a total of 100 samples, the probability that this specimen will fail within 4,391 load cycles is 25%, since statistically 1 out of 4 samples will have failed by that time. The relative frequency of failure can therefore be directly interpreted as the probability of failure. As we have just seen, we can determine the probability of fracture by dividing the number of failed samples at a given time by the total number of samples. In the case of the last sample, we then inevitably get a failure probability of 100%, since all the specimens examined broke at this number of load cycles. This must not be generalized at this point. This means that we must not assume that all samples will break at 15,565 load cycles at the latest in further tests. If, for example, we had carried out the fatigue test on 200 samples, it is highly probable that one sample would have survived 20,000 or more load cycles. Conversely, if the fatigue test had only been carried out on 5 samples, and one sample had survived a maximum of 5,000 load cycles at best, this would of course not mean that this could be applied to all the other samples to be tested. In statistics, therefore, a distinction must always be made between the population of all possible specimens, which in this case is in principle infinite, and the statistical sample, which is a representative subset of the population and from which conclusions are then drawn about the population. Since the fatigue test does not test the entire population of all possible specimens, but only a more or less representative statistical sample, the failure frequency is systematically too high because there is always some probability that an untested specimen will survive more load cycles than tested with the statistical sample. For this reason, the total number of specimens is often corrected by the value 1 when calculating the failure frequency or failure probability. This corrects the failure probability for all samples to lower values. In particular, the failure probability for the last specimen is no longer 100%, but is reduced to 95%. This allows samples to survive more than 15,565 load cycles with a probability of 5%. This is more realistic than the assumption that all samples fail at this number of load cycles at the latest. Note that the aim of the fatigue test and basically of every statistical evaluation is not to describe the statistical sample as accurately as possible, but always to describe the population. By correcting the statistical sample, we get much closer to the population. In addition to the correction formula just described, there are other such approximation formulas. What they all have in common, however, is that they correct the probability of failure of the specimens to lower values. The graph also shows that the correction becomes more significant as the number of load cycles increases. However, for small numbers of load cycles the correction remains negligible. It should also be noted that the sum of the samples corrected by 1 has a large influence for small sample sizes. If, on the other hand, 2,000 specimens were used instead of 20, the influence of the correction would be negligible, because it makes little difference whether the failure frequency is calculated with a denominator of 2,000 or 2,001. This is also not surprising, since with such a large sample size we would already have a much more accurate picture of the population, so there is no need for a large correction. Let us take a closer look at the cumulative failure probability. The graph shows the probability that a specimen will fail within a given number of load cycles. For example, we can see that the probability of a specimen breaking within the first 3,000 cycles is approximately 20%. If the probability of failure is 50%, half of the specimens will have failed after approximately 6,200 cycles. However, due to the small sample size of 20, it is difficult to give a valid figure for the number of load cycles that can be survived. It may well be that the 50% failure probability is closer to 5,000 or 8,000 cycles. In order to be able to state such a failure probability more precisely, countless samples would have to be tested. This is not possible in practice for economic reasons. Therefore, the cumulative probability has to be determined mathematically from the measured data. The Swedish engineer and mathematician Ernst Weibull thought about this in the middle of the 20th century. He proposed the Weibull distribution named after him for questions about material fatigue and the failure of electronic components. The shape and scaling of the given Weibull function is determined by two parameters. The shape parameter k determines the basic shape of the curve and is also called the Weibull modulus. The scale parameter, symbolized by the capital letter T, only stretches or compresses the curves so that they can be adapted to the variable plotted on the horizontal axis. This plotted quantity is symbolized in the Weibull function by the lowercase letter t and corresponds in our case to the number of load cycles and in the general case to a time. We will therefore often use the term time synonymously for the number of load cycles. The diagram shows the Weibull distribution function for different shape parameters k, with a scale parameter t equals 7,800. It can be seen that this scale parameter describes the intersection of the curves and thus determines their position. We will also see later that this scale parameter always corresponds to a failure probability of 63.2%. It can be seen from the diagram that the chosen scale parameter of 7,800 and the shape parameter of 1.6 reflect the cumulative failure probability for our statistical sample very well. How these parameters are determined from the measured data will be explained in detail later. At this point, we will first focus on the handling of the distribution function. With the help of this Weibull distribution function, we can now determine more concretely with what probability a fracture of a specimen will occur at a certain number of load cycles. For example, if we want to know the probability of a specimen breaking within the first 4,000 load cycles, we set the value 4,000 for the variable t and calculate the corresponding probability f. In this case, the probability of failure is 0.29, that is 29%. Thus, on statistical average, 29 out of 100 samples will break within the first 4,000 load cycles. Conversely, we can now also determine the number of load cycles at which, for example, 50% of the samples have failed. To do this, we need to solve the distribution function for the variable t. To do this, we put the exponential term on the left side of the equation. Then we apply the natural logarithm function to both sides. Using the logarithmic identity shown, we obtain the given equation. We can now use another logarithmic identity to eliminate the negative sign. We now solve this equation for the variable t and obtain the shown formula. With this formula, we can now determine the number of load cycles for a certain probability of failure. If we assume the above-mentioned fracture probability of 50%, we obtain 6,219 load cycles. This fracture probability of 50% then ultimately serves as the value for the point on the Wöhler curve. The question now arises as to how to determine the shape and scale parameter from the experimentally obtained data. Simply guessing the parameters so that the Weibull curve passes through the data points as accurately as possible is not only time-consuming but also inaccurate. Moreover, spreadsheets usually do not offer tools for analyzing such complex curves. It would be much easier if the data had a linear relationship. In this case, linear regression could be used to determine the relationship. To achieve exactly this, the measured values plotted in the diagram must be converted into a linear representation. To do this, the Weibull function needs to be represented differently. This is done in the following. To do this, we first rearrange the equation so that only the exponential function is on the right-hand side of the equal sign. Then we apply the natural logarithm function to both sides. Now we use the logarithmic identity shown to simplify this equation. We can now use another logarithmic identity to eliminate the negative sign. This gives us the equation shown. Then we use the natural logarithm function again on both sides of the equation. We can simplify the right side with the given logarithmic identity as shown. Finally, we use the logarithmic identity shown and get the given equation. This equation looks rather complicated at first glance, but it has a crucial advantage. This is because this equation represents a straight line if we plot the logarithmic time, or in our case the logarithmic number of load cycles, on the x-axis and the double logarithmic expression for the cumulative failure probability on the y-axis. If we choose such a diagram for our data, the slope of the linear regression line corresponds exactly to the Weibull modulus. The scale parameter can then be determined from the y-intercept by using the Weibull modulus. Using our measurements as an example, the procedure for determining the two parameters of the Weibull function is shown in the following. To obtain a linear representation of the data, the number of load cycles is first logarithmized. Then the double logarithmic term of the cumulative probability is determined for each number of load cycles. The cumulative probability must always be given as a decimal number and not as a percentage. We can now use a spreadsheet to plot the values. Such a graph is also called a Weibull plot. In this Weibull plot we can display or calculate the equation for the linear regression line. In our case, we obtain the equation shown. At this point, we can also check whether the distribution is indeed a Weibull distribution or whether some other form of distribution needs to be chosen. If the points were not close to the straight line, but were more widely scattered, then another form of distribution would have to be chosen. In our case, the Weibull distribution seems appropriate, although more data would be needed to make a valid statement. However, using the equation of the linear regression line, we can now determine the shape parameter directly from the slope. The Weibull modulus in this case is 1.61. From the y-intercept b, we can now also determine the scale parameter t by using the shape parameter k. We will derive the required formula for this in the following. First, we rearrange the given equation as shown. We now use the exponential function as shown to calculate the scale parameter using the y-intercept b and the Weibull modulus k. In this way, we obtain a scale parameter t equals 7,807 in our case. We have now determined our two parameters for the Weibull distribution. On the basis of the Weibull line, we can basically only make statements about the failure probabilities of the examined statistical sample. Generalization to the population is not possible without further ado. If we were to examine a second statistical sample, the Weibull line we would obtain would be more or less different from the first. For this reason, the graph is often extended to include a confidence interval. The confidence interval indicates the limits within which the Weibull line can be expected to lie and the probability with which it reflects the failure probabilities of the population. With a 90% confidence interval, the Weibull line has a 90% probability of being in any position within the confidence limits. The determination of such a confidence interval is not discussed in detail here for reasons of complexity. Let us now look at the Weibull function itself a little more closely. From the argument of the exponential function, it is clear that the scale parameter must have the same unit as the variable t, since an exponent cannot have a unit. In our case, the scale parameter therefore has the meaning of a number of load cycles. If we use this scale parameter as the variable t in the Weibull function, we obtain a probability that is characteristic for the scale parameter. It is always 0.632, independent of the Weibull modulus. We can therefore interpret the scale parameter very graphically as a lifetime where the probability of failure is always 63.2%. This is why the scale parameter is often referred to as the characteristic lifetime. In addition to the cumulative failure probability, the Weibull distribution function can also be used to produce the aforementioned probability plot, which shows the probability of a sample failing within a given range of load cycles. As mentioned earlier, such a diagram results from the derivative of the distribution function. We therefore differentiate the Weibull distribution function with respect to the variable t. Since the derivative of a constant is 0, we only need to calculate the derivative of the exponential term marked in red. By using the chain rule, we obtain the shown equation. We use the chain rule again and get the following equation. Finally, we obtain the given function for the derivative of the Weibull distribution function. This function is also known as probability density function. The diagram shows the course of the density function for a scale parameter t equals 7,800 and a shape parameter k equals 1.6. In such a diagram, the area under the curve corresponds to the failure probability of a sample within the considered interval. In this case, for example, between 6,000 and 8,000 load cycles, the area under the curve is 0.165. In concrete terms, This means that a sample has a probability of 16.5% to fail within 6,000 to 8,000 load cycles. For any interval, the probability of failure can be obtained from the integration of the density function. This is simply the difference in the respective cumulative probabilities. As already explained, the Weibull modulus has a decisive influence on the shape of the Weibull curve and thus on the characteristics of the failure processes. Compared to the Weibull distribution with a shape parameter of 1.6, the dashed curves show a failure behavior with a Weibull modulus of 6.0. It is immediately apparent from the probability density distribution that the specimens fail in a much narrower range. The load cycles to failure are therefore less scattered in this case. The dispersion of such values is described by the average deviation from the arithmetic mean. To determine the arithmetic mean, we first add up the randomly distributed load cycles and divide this value by the total number of samples. With a total of 137,993 load cycles to failure and a total number of 20 samples, this results in 6,900 load cycles at which the samples fail on average. This is generally referred to as mean time to failure. Around this mean value, the actual failure times, or in our case, the number of load cycles to failure of the individual samples vary to a greater or lesser extent. This dispersion around the arithmetic mean value is described by the so-called variance or standard deviation. The sample variance corresponds to the mean value of the squared deviation of the random variable from the arithmetic mean. In our case, we determine the empirical sample variance by first calculating the difference to the arithmetic mean for each load cycle to failure. These deviations are then squared. This has the advantage that the signs of the deviations are no longer important and that large deviations are taken into account much more than small ones. We then add up the squared deviations and divide this sum by the total number of samples. In our case, this gives us a mean squared deviation from the arithmetic mean of about 13 million. Taking the root of this variance gives the standard deviation as a measure of the dispersion of the random values around the arithmetic mean. In our case, the number of cycles to failure varies by an average of 3,772 cycles around the mean time to failure of 6,900 load cycles. Both the mean value just calculated and the standard deviation refer only to the statistical sample. A generalization to the population is not possible without further ado. If one were to carry out the fatigue test again with the same number of samples, one would certainly obtain a somewhat different mean value. However, the more tests that are performed, the closer the empirically calculated arithmetic mean of the statistical sample gets to the true mean of the population. This actual mean value of the population is then called the expected value. For random variables, if the population is assumed to follow a Weibull distribution, the expected value can be calculated using the shape and scale parameters as indicated. Gamma is the so-called gamma function. The sample variance or sample standard deviation also refers only to the statistical sample. But here too, if the random variables are distributed according to Weibull, the standard deviation of the population can be determined by the shape and scale parameters as indicated. In the following, the Weibull distribution is considered more generally under the aspect of the service life of components. With such a distribution, the failure of mechanical or electrical components can generally be described as a function of the operating time. This assumes, of course, that component failure follows the Weibull distribution, which is assumed in the following. The graph shows the typical probability of failure as a function of operating time, as obtained by the fatigue test. Instead of stating the probability of failure of components, it is also common in practice to state the probability that components will survive a given time without damage. This is then referred to as reliability or survival probability. For example, in a fatigue test, if the probability of a specimen failing within the first 3,000 load cycles is 20%, this means that the probability of the specimen not failing within the first 3,000 cycles is 80%. The survival probability R and the failure probability F are thus linked as indicated. This finally results in the shown survival function, which is also called the reliability function. The diagram shows the course of the survival function, which is only mirrored vertically compared to the failure curve. The reliability curve indicates the number of components that are still fully functional. For example, if we could test 200 samples simultaneously in the fatigue test, after 4,000 load cycles 70% would still be without fracture, that is 140 samples. After 5,000 load cycles, 60% of the samples would still be without fracture, that is 120 undamaged samples. After 10,000 load cycles, there would still be about 40 specimens without fracture, and after 11,000 load cycles, there would still be around 30 undamaged specimens. When it comes to characterizing the service life or the reliability of components in general, the so-called failure rate plays an important role beside the survival probability. The failure rate indicates how many components fail per unit time. In the case of the fatigue test just described, for example, from 4,000 load cycles, 20 specimens fail within the next 1,000 load cycles. The failure rate for this period is therefore 1 specimen per 50 load cycles, or, purely mathematically, 0.02 specimens per load cycle. It should be noted that this failure rate only applies to the specific period between 4,000 and 5,000 load cycles. In other time periods, other failure rates result. For example, in the period between 10,000 and 11,000 load cycles, only 10 specimens fail. The failure rate for this period is therefore 1 specimen per 100 load cycles, or 0.01 specimens per load cycle. On the face of it, the comparison of the two failure rates suggests that the probability of failure decreases as the number of load cycles increases because fewer and fewer samples fail. However, this somewhat contradicts everyday experience. Experience shows that more rather than fewer components fail with increasing service life. The reason for this apparent contradiction is that we must not look at the absolute failure rates in terms of the components originally present at the beginning, but must relate the failure rates to the currently intact samples. Let's take the example of the specimens from the fatigue test again. It shows that after 4,000 load cycles, 140 samples are still undamaged. Out of these 140 samples, 20 samples fail within the next 1,000 load cycles. Based on these 140 intact samples, about 14% fail during the considered time period. The relative failure rate in this case is therefore 14% per 1,000 load cycles, or 0.014% per load cycle. If, for example, we still had 100,000 intact samples after 4,000 load cycles, 14 samples would fail with each subsequent load cycle. Of course, it should be noted that the failure rate in principle already changes with the next load cycle, and this statement is therefore only valid in a very limited range. Let us look at the time of 10,000 load cycles. At this point, only 40 of the original 200 samples are still undamaged. In the next 1,000 load cycles, 10 samples fail. In relation to the original number of 40 samples, this means that 25% failed. The failure rate in this case is therefore 25% per 1,000 load cycles, or 0.025% per load cycle. If, for example, we still had 100,000 intact samples after 10,000 load cycles, 25 samples would now fail with each subsequent load cycle. The relative failure rate is thus a measure of the probability of failure at a certain point in time when the component has not yet failed. The failure rate, so to speak, takes into account the history of components, and how long they have been in use and how likely a failure is at this point in time. We can thus see that this so-called relative failure rate increases with increasing service life, as it becomes more and more probable that a component that has not yet failed will eventually fail after such a long time. For this relative failure rate, we must therefore always relate the absolute failure rate to the number of components still present at the point in time t we are considering. When we talk about the failure rate in the following, we always mean the relative failure rate. In the following, the formula for calculating the failure rate at any time t is derived with the help of the Weibull distribution. For this purpose, an arbitrary time t and a time span delta t are considered. Instead of defining the failure rate by the absolute number of samples n as before, the relative number of samples can also be used in the form of the survival probability shown in the diagram. Note that both quantities ultimately differ only by a constant factor, namely the number of samples originally present. Furthermore, for the percentage delta r of samples that fail within the time delta t, it is irrelevant whether one calculates this with the survival probability r or with the failure probability f. The difference of the surviving samples corresponds directly to the difference of the failed samples. If, for example, the number of intact samples decreases by 10%, the number of failed samples obviously increases by 10% as well. Note that we have always related the cumulative probabilities to the initial number of samples and not to the number at any given time t. In the definition of the failure rate, we therefore use the failure probability delta f instead of the survival probability for the period delta t. The quotient of the failure probability delta f and the time delta t corresponds to the slope of the cumulative failure probability curve in the graph. Thus, for infinitely small time intervals dt, The failure rate at any given time t is the slope of the tangent of the failure probability curve divided by the survival probability. Since the slope is mathematically equivalent to the derivative of the corresponding function, we now use the derivative of the failure probability function to express the failure rate. We have already seen that the derivation of the failure probability function leads to the failure density function. So we see that the failure rate is equal to the quotient of the failure density function and the survival function. In this way, we obtain the shown formula for calculating the failure rate, which is also called the hazard function. The diagram shows the course of the cumulative failure probability and the course of the failure rate with increasing time or load cycles. In summary, let us look again at the time of 6,000 load cycles. From the probability curve, we see that at this point 50% of the original samples have failed. Based on the failure rate of 1.75 times 10 to the power of -4, we can also see that at this point 0.0175% of the samples currently still present will fail per load cycle. Let us now look at different Weibull functions in the respective plots of the cumulative failure probability, the failure density, and the failure rate. The graphs first show the curve for a Weibull modulus of k equals 1.6. In general, the failure rate increases for a Weibull modulus between 1 and 2, but less strongly with increasing time. With a Weibull modulus k greater than 2, on the other hand, the failure rate increases more and more. In the present case, the Weibull modulus is chosen in such a way that an almost symmetrical density distribution results, as is typical for a normal distribution. In this way, with a Weibull parameter of k equals 3.6, a Gaussian distribution can also be achieved in a very good approximation. If, on the other hand, the Weibull modulus is smaller than 1, the failure rate decreases steadily. A special case arises for a shape parameter of k equals 2. In this case, the failure rate increases linearly with time. Another special case results for a Weibull modulus of k equals 1. In this case, we get a constant failure rate. When describing the reliability of components, it is usually not possible to describe the entire phases of the service life with a single Weibull distribution. Rather, depending on the phase, different Weibull functions are used. Let's look at the life phases of a drilling machine as an example. A lack of quality control during production can initially lead to many early failures. This can be due to material, production, and assembly errors, for example. In this case, a lot of drilling machines will fail at the beginning, which means a high failure rate. After the defectively produced drilling machines have failed, only the faultlessly produced drilling machines will have survived after some time. This phase of early failures is typically modeled with a Weibull modulus of less than 1. Once the early failures have sorted themselves out, the failure rate changes to a more or less horizontal curve. In this case, the failure probability of the still intact drills does not depend on time, but is relatively constant over a long period of time. This is the random failure phase. These failures may be due to operating or maintenance errors, for example. This random failure phase is typically modeled with a Weibull modulus of about 1. Over time, however, the wear on the components of the drilling machines inevitably increases, and for example, the bearings start to wear out or other mechanically stressed components begin to fail. The drilling machines have reached the end of their service life. In this third phase, failures due to fatigue and wear increase again. The Weibull modulus is greater than 1 in this last phase. Due to the typical course of the failure rate, such a graph is also called a bathtub curve. Lastly, the Weibull distribution for various shape parameters is to be considered once again. What all distribution forms have in common so far is that there is a certain probability of failure immediately after the start of the service life. In some cases, however, there is a failure-free period below which failure is not to be expected. This is the case, for example, with brake discs, which first wear continuously and thus always have a certain failure-free time before they are worn out and threaten to fail. Such a failure-free time can also be taken into account in the Weibull functions if they are extended by the failure-free time t0 as indicated. However, it should be noted that the representation in the Weibull plot no longer results in a straight line, but in a curve. At the point of the logarithmic failure-free time, the curve forms a vertical line. In this way, the failure-free time can be determined from the measured values. To determine the shape and scale parameter, the time must first be transformed using the failure-free time as indicated. In this way, a straight line is obtained again. The slope again corresponds to the Weibull modulus, and from the y-intercept the scale parameter can be determined. In contrast to the formula already derived, The formula for determining the scale parameter must be extended by the failure-free time in this case.